sampling and quantization of signals, which will be the first step to talk about digital communication. So why are we talking about digital communication? So far, we've studied analog communication. However, as you know very well, most of communication today is digital. So first of all, what do we mean by digital communication? Analog signals take continuous values, and digital signals take values from a finite set. That's the main difference. Specifically, we often deal with binary signals in computing and in communication. Binary signals take two possible values. And as a result of these two possible values, Boolean logic is applicable. Okay. Incidentally, the application of Boolean logic to electronic circuits was first proposed by Claude Shannon, who is the inventor of information theory, in his master's thesis. And this made digital computers possible. Thus, it can be seen as the start of modern computing. And we could go as far as to say that that really kick-started the information age. Now, in digital communication, if you have a source which you can characterize it as a digital source, it outputs a sequence of numbers. And each of these numbers, x1, x2, and so on, come from a finite set of values. Okay. Now, often the source is modeled as a random source. It creates a random process. So the xi's, the source output values, have a probability distribution. They're modeled to have a probability distribution. Now, basically, the more randomness the xi's have, the more entropy, essentially, and this can be made precise later. The more rate in bits per second we need to represent this source, to transmit the values of the source. I mean, as an extreme example, to make this a little bit maybe understandable to you, if the source always put out a single value, fixed value A, okay, how many bits would you need to transmit this information? 0. Once you transmit the A once, it is sufficient for the future. So you wouldn't need any rate in the long run in terms of bits per second to convey the output of this deterministic source in this very extreme example. Okay, so if you can go from this, if every sequence value is either A or B, equal probably, right? Think about how many bits of information is needed to transmit the source. Okay. Now, our computers and other digital devices, sensors, switches, routers, etc., they always work with binary information. So in most communication scenarios today, the source data is already digital, right? The source comes from, it could be a video playing on your application, for example, that is already produced as a digital source. However, for analog sources, okay, for analog sources, we obtain these discrete values through sampling the source. And sampling is a very, very fundamental idea that you have studied in your signal processing course, introductory signal processing course before. With communication, it will possibly take on a new meaning for you. And in our day and age, today, as we are more and more interested in remote sensing and control and tracking and monitoring, we are as much as ever dealing with this problem of when to sample, especially when we're sending these samples across a network. Okay, but let's go back to the basics at the moment and see the fundamental theorems about sampling and quantization. So now, once you sample values from an analog source, we could, model these values as real numbers, but we cannot really represent real numbers by choosing values from a finite set, unless we make a rule for how to map these real numbers to the values of the finite set. This rule is called quantization. Okay, so the quantization is the mechanism of going from analog signal values to discrete signal values, and or maybe digital signal values, and then you go and one step further and convert these digital values to binary values. Okay, and obviously, as this is a lossy process, there's going to be a trade-off between the rate of compression and distortion. Okay, there is a theory that deals with the limits of rate for a given tolerable distortion, and this is called information theory. Now, today's digital communication systems, as I said, mostly employ digital transmission of information, which allows us a lot of flexibility in communicating over long distances without loss of quality, because once you decode a sequence of bits, you can completely retransmit them in any medium that you want. For example, you may be receiving you may be receiving a packet on a wireless link, but then once you decode it, you can go ahead and then forward it over an optical fiber, etc. And sending data in a multi-hop fashion across different physical channels over the internet, etc., is made essentially very, very organized through digital communication. And to me, it's quite unthinkable to try and do it using analog communication. Okay, so basically digital communication appears to be essential to the current internet architecture. Okay, now in analog communication systems, the main performance criterion is fidelity. How well does the demodulated signal approximate the original transmitted signal? And, we could come up with qualitative or maybe quantitative criteria for this reproduction, but it's usually difficult. In digital communication systems, the success metric is quite clear. Essentially, we want the decoded message to be exactly equal to the transmitted message sequence. Okay, we want the decoded sequence of bits to be exactly equal to the transmitted sequence of bits, with probability very close to 1. Now, how close to 1? It depends on the system. Sometimes we can tolerate a bit error rate around 10 to the minus 4, for example. But sometimes for other systems, for example, in the ultra reliable low latency mode in 5G, the bit error rate criterion is around 10 to the minus 9, okay, which is very, very small. So basically reliability is characterized very easily by the concept of bit error rate or bit error probability. Now, what is the bit error probability? It's the probability. It's essentially, if you focus on a single bit, the probability of error, bit error, is the probability that 0 was sent and 1 is decoded, or 1 is sent and 0 is decoded. Okay, usually the probabilities of sending 1 and 0 are equal. I'm sorry. Hence, basically, the probability of these two terms are equal. Now, of course, why do we make errors? The main reason is noise in the receiver structure. And the probability of making an error under noise depends on the signal to noise ratio. It also depends on the data rate, because if your data rate, if you can afford a low data rate, you can use a low rate code, which means you protect your bits by transmitting a large number of symbols, okay, for a given sequence of bits, and that will increase the probability that you get it right at the expense of lowering the data rate. So error probability depends on the signal to noise ratio and the data rate. Okay, and the signal to noise ratio, of course, depends on many factors, including the transmit power as well as attenuation in the channel, etc. But sometimes the channel is characterized by more than just attenuation. The channel essentially has a probability, a conditional probability function, which means that sometimes the zeros that you sent are distorted and turned into ones, and ones are turned into zeros with certain probabilities. That characterizes our channel. So in digital communication, the channel is really characterized by a probability mapping. Okay, but we'll say more about that later. Okay, now as I said, digital information can easily be encoded, encrypted, stored, retrieved, switched with electronic or optical components, and sent in real time across networks. Information can be stored digitally with as small loss as desired, as far as you allow yourself coding, and it can be transmitted as reliably as desired. Of course, there are trade-offs, as I said. The more reliability you need, that requires, coding, which may reduce the rate. Okay, fundamental limits for compression and transmission of information are provided by information theory, and in our department, this is studied in the course EE 533, which is offered in the spring. Okay. Now, however, everything, all of this digital communication starts with the sampling theorem. So let's talk a little bit about the sampling theorem. Now, we start with a continuous time signal. Okay, and consider multiplying it by an impulse train. You all know what an impulse train is. basically they are impulses placed evenly, and of course the impulses, you know, have in this case have equal weight. But not make a misrepresentation. And if you mathematically multiply a signal with an impulse train, of course, this is not anything that you do nobody does this in real life, but this is a mathematical concept. If you were to take the signal in continuous time x of t and multiply it by an impulse train, what would you see in frequency domain? In frequency domain, an impulse train is equivalent to an impulse train in frequency. Okay, except the locations of the impulses are separated by 1 over t0, where t0 is the sampling period. Okay, but then this corresponds to, in frequency domain, convolving the spectrum by an impulse train, which means replicas of the Fourier transform of the original signal occurring at multiples of 1 over the sampling period. Okay, I think there's a typo here. All right, so you all know this from previous classes. Okay, so provided that there's no aliasing here, meaning provided that the sampling period is at least twice as big as this W, then this sampling operation is recoverable. So there is no loss of information. Many people worked on the sampling theorem essentially around the same time, around 1930s. Sometimes the first instance of the sampling theorem is said to be generated by Kotelnikov, but it is related to the work of Nyquist in 1928, where he was worrying about how many telegram pulses, band limited to W, can be sent per second without any simple interference. And the sampling theorem was proved independently in one form or the other by various researchers. However, Shannon, in his 1948 paper where he defined information theory, where he constructed the mathematical theory of communication, he started by very elegantly proving the sampling theorem. And that's the version that we are going to review here. Suppose x of t is band limited to W, or essentially, alternatively, its power spectral density is band limited to W when we talk about a random signal. If we sample at intervals Ts, where 1 over Ts is much less than 2W, so the sampling rate is much less, sampling rate, so there's a typo here. So the sampling period, sampling rate, 1 over Ts, must be bigger than 2W, right? So there's a typo here. Then the signal can be reconstructed from its samples. Okay, so we can use impulse sampling to show a very simple proof, as we just argued in the previous slides anyway. Impulse sample the signal, think about the result in frequency domain, and we have a number of copies of the signal shifted. Okay. Now, if 1 over Ts is much larger than 2W, then the replicas of X of F will not overlap, and therefore we can low pass filter the sampled signal to recover X of T. Okay, so basically, if 1 over Ts, so this is 1 over Ts basically, and this is W and W. As long as 1 over Ts is larger than 2W, then there will not be aliasing, and we can low pass filter the sampled signal. Okay, now low pass filtering corresponds to multiplying by this ideal rect filter, whose impulse response is a sinc pulse. Okay, now the recovered signal is then the convolution of these sinc pulses, of the sinc pulse essentially, with the impulse sampled waveform. What is this in time domain? When we do this convolution, of course, we get rid of the impulses. Now we're talking about something really physical. These are samples, okay? These are real values, okay? Multiplied by sinc pulses that are shifted by multiples of Ts, the sampling period, okay? This is called sinc interpolation, ideal sinc interpolation. So what is this telling us? It's telling us something really quite physical. It says, take samples from the signal, take samples, oops. These are samples, and take a bunch of shifted sinc pulses, okay, repeated every Ts, and for each sinc pulse, weigh it with the corresponding sample value. When you sum up the sinc pulses, you get the original signal back, as if you have the full information about the signal. There's no loss of information through the sampling. Okay. To ensure this, of course, you can pre-limit the bandwidth of your signal before sampling, and that is called an anti-aliasing filter. Now, practically, of course, practically nobody uses sinc pulses, right? Now, first of all, as an exercise, I will ask you to think about the following. We don't always have low pass signals. Sometimes we have band pass signals. Okay, think about a band pass signal like this, that is, whose power spectral density is limited to 2W. Okay, but this FC, let's say this is FC. FC is very large, okay? So it's a band pass signal located at FC, and it has bandwidth 2W. Okay. Now, how much rate do you need to sample this signal? What is the rate you need to sample and recover this signal? Is it, would you consider that this signal is essentially band limited to FC plus W? Hence, you need to sample at 2 times FC plus W or faster. Of course, it will work if you sample at twice FC plus W, but this is too much. This is excessive. So I will ask you to show in spectral domain, and this is really going to be easy when you draw it in spectral domain, that sampling at 2W is sufficient. Okay, so we can extend the sampling theorem to bandpass signals as well. Now let's go back to the practical issues. Impulse sampling or sinc interpolation are not realizable. Why? Because they require essentially a perfect filter, a perfect impulse response. And the sinc as an impulse response is unlimited in time. Right. So in practice, zero order hold or sample and hold is the commonly used A to D conversion technique. So this is equivalent to cascading impulse sampling with a rectangular impulse response, just a rectangular pulse, that is. Now, I think there was an interruption. We can continue. Okay, so now, sample and hold. This means read the sample value from the signal and keep it until the next sampling interval, and then read the next sample value and keep it. So as an operation, this is equivalent to following the impulse sampling by this pulse, basically rectangular impulse response. Okay. And the result is this staircase-like function. Okay, you can think of it as a staircase type function. Now, how do you reconstruct from zero order hold? Well, it's very simple, really, because, what do you want mathematically to recover from the impulse sampling? You need an ideal rect filter. So if you follow this HO of t by an HR of t, such that the resulting effect of the two filters cascaded together is an ideal rect, then you're done. But since the Fourier transform of this H0 of f is a sinc function with a linear phase due to the time shift, HR of f is given by 1 over that sinc characteristic, which pretty much looks like this within the given bandwidth.